Feels a little wintry after yesterday felt so spring-like.
Yeah, it was like the first day that actually felt like
Right? Yeah. I was like, wait a minute.
And then
Like,
that great.
they're psyching us out.
Got a little cast.
Keeping you on your toes. Yeah. Make sure I have my ringer off. Ringer off. All right, well, we have one more example on this page where we're doing the log limit process. So the idea with the log limit process is that if we have an indeterminate form of the 1 to the infinity type, that's when we use log limit. So if we have an indeterminate form, 1 to the infinity, so in this example that we did on Tuesday, the inside here, the base of this exponential expression, or this, this thing here, it's not really when we define an exponential has a very specific definition. The base has to be an integer greater than, or it's got to be a number greater than 0 but not equal to 1. That's the formal definition of an exponential. But you know what I mean. It's a power expression. So that's the base of this power expression. Technically, we shouldn't call it an exponential expression, but a lot of times we do anyway. But this expression here, the base of it, that goes to 1, and then the exponent goes to infinity. So it's a 1 to the infinity type of indeterminate form. And so process again, we create a function, take the log of both sides. Once we take the log of both sides, we can pop the exponent down using a log property. Once we pop that exponent down, then we take the limit of both sides. On the left-hand side, the limit is in front of a log function. Log function's a continuous function, so the limit can move to the inside, which is something that you do all the time, maybe not even thinking about it. Like if you have something like the limit of 2x plus 1 to the 5 as x goes to 3. Don't you just plug the 3 in here? But what you're really doing is saying, oh, the fifth power function, that's a continuous function. So technically what you're doing is moving the log inside the fifth power function, and you're taking the log, the limit of the inside, and then you're applying the 5. So you do this all the time where you move the limit through continuous functions, but most of the time we don't actually write it because it's kind of a tedious step. Most of the times we would just plug the 3 in and get 7 to the 5th. Right. So that's what's happening though. You are moving the limit symbol through a continuous function when you do those things. It's a little more kind of pronounced here where it's like, oh, okay, the limit's going to move to the inside of the log. Which again, we do that all the time too. If we were taking the limit of natural log of x as x goes to 1, none of us really write, usually, it's very rare that you would write this, the limit of x as x goes to 1, but you don't move it to the inside normally. If you have a limit at a constant, you would just write here, plug that constant in and say, oh, natural log of 1 is 0, so the limit is 0. Right? But that's what's happening. So you do it all the time, but here we need to do it because we don't have something we can evaluate right now. We can't just plug something into the y, so we're trying to move it inside so that we can solve for this expression, limit of y. And then all of these 1 to the infinity things, they're going to lead us to a L'Hopital's rule. So once we get to L'Hopital's rule, you need to make sure you know how to take the derivative of a log function. Derivative of a log is flip the inside, multiply by the derivative of the inside. If the inside is a quotient, you have to use a quotient rule. And at the very end, we have to exponentiate to solve for limit of y. So that process is what we're going to use every time we have a 1 to the infinity. So let's do another one from start to finish. So right here, we're taking the limit of this, and we see that, oh yeah, if we take the limit of the inside, that becomes a 1. And the exponent goes to infinity. So this is a 1 to the infinity indeterminate form. So we are dealing with that indeterminate form. So first step, we define a function. You don't have to, but I tend to make it a function with an x because I know we're going to take a derivative. And technically, you can't take the derivative of a sequence because that's not a continuous function. But if you want to use n's, that's totally fine if you want to use n's. So then we take the log of both sides. And remember, in calculus, when we say take the log of both sides, we mean the natural log. If there were some reason to use a common log or a log with a different base, it will be obvious. 99% of the time, when we are dealing with logs, we are dealing with natural logs. That is the log function that we are going to use. So we pull the x down after taking the natural log of both sides. Then we are going to take the limit of both sides. And on the left side, we are going to move that limit to the inside right away. It's just going to be easier to move it in right away. We don't need to write an extra step. And then on the right-hand side, we kind of know they're all the same. We want to create a L'Hopital scenario. So we're going to need to manipulate the right-hand side so that we have infinity over infinity or 0 over 0. Like if you glance at it ahead of time, you see that this is going to be infinity times 0. And anytime you have that indeterminate form, you just push one of the functions into the denominator to create an infinity over infinity or a 0 over 0. It doesn't matter which one. And what we will, I don't want the y there. What we will do is, in our case, it's a lot easier to put the x into the denominator than the natural log into the denominator. Although you could push the natural log into the denominator if you wanted and get the other indeterminate form, infinity over infinity. But this one tends to be easier. And has everybody seen that multiplication by x is the same thing as division by 1 over x? If you're dividing by 1 over x, it's the same thing as multiplying by x. Right? Those are equivalent. So now we have the indeterminate form 0 over 0. So I'll indicate that with just a pair of zeros right there, just as a heads up. OK, we're going to use L'Hopital's rule now. We have a 0 over 0. That's an indeterminate form that we can deal with via L'Hopital. Remember that L'Hopital's rule, it's a super intuitive thing. If we have a ratio of functions and we're trying to take their limit, all we're doing is saying the ratio of functions is going to approach the same thing as the ratio of tangent lines. If the tangent line is the best approximation for each of those functions individually, then the ratio of tangent lines should do the same thing as the ratio of functions. If it didn't, that wouldn't be a very good approximation. So that linear approximation, that derivative, the quotient of derivatives is going to do the same thing as the quotient of functions. So we have to take the derivative of top and bottom. All right, derivative of the denominator, that's the easy one. We have x to the negative 1, negative x to the negative 2, when we take the derivative. X to the negative 1, bring down the exponent, subtract 1 from the exponent, rewrite it without a negative exponent. OK, the numerator. Log function. To take the derivative of a log, we flip the inside. It's 1 over the inside. So that's the first step. 1 over the inside times the derivative of the inside times the derivative of the inside. The derivative of the constant 1 is 0. The derivative of 4x to the negative 1. Negative 4x to the negative 1. So we're differentiating that. Let's think of it in our mind like that. Negative 4x to the negative 1. The derivative, we bring down the power. We get 4, subtract 1, and then we write it without any negative exponents. Usually easier to cancel stuff without any negative exponents. So that'll be 4 divided by x squared. Now we have to simplify using algebra. So let's do this. Let's write it like this. So I'm going to think of it as this factor times that factor, and then this factor is going to get flipped upside down. Dividing by a fraction means multiplying by the reciprocal. So here is how I'm going to write it. So the first one, I need to simplify. I don't want a fraction within a fraction. Right? That's a complex fraction. So to clear that fraction out there, we are going to come in here and multiply the numerator and the denominator by x. Right? You multiply by that common denominator, and that will clear out the fractions. So if we multiply the top by x, we get x. Multiply the bottom by x, we get x minus 4. So that's that one. And then we have the 4 over x squared. And then we're flipping this one, so we have negative x squared over 1. And then we have a bunch of cancellation. Maybe not a bunch, but we have cancellation. So we will have limit of the x squareds cancel. So it looks like we end up with negative 4x divided by x minus 4. And then this limit is as x goes to infinity. And what is that limit? Negative 4. So we have 3 ways to evaluate that limit, whatever floats your boat. You can look at that and go college algebra and say, hey, those are polynomials with the same degree. So the limit is the ratio of leading coefficients. That's the limit at infinity technique from college algebra. If they have the same power, the ratio of coefficients is what the function is approaching. You can use the Calc 1 approach, divide L'Hopital's rule. You can take the derivative of top and bottom. Derivative of top is that, derivative of bottom is that. You could do that. The third way is to divide by the highest power of x. It does not matter. There are 3 ways that you could do that. And that limit will be negative 4. So whatever your favorite limit approach is, you have 3 choices right there. Divide by the highest power of x. Usually the highest power of x from the denominator makes the most sense. You can take L'Hopital's rule, derivative, or you can do leading coefficient technique. Doesn't matter. All the same. Now, the goal is to find the limit of this thing. And this thing up here is what we decided to call y. So that's what we called y. So we want the limit of that as x is going to infinity or n is going to infinity. So on the left side, that's what we have here. We have limit of y right there, but we have to unravel that natural log. So what do we do to both sides? Yeah, we're going to exponentiate both sides. So the limit of y as x goes to infinity is going to be, we exponentiate that, we get e to the negative 4. All right, any steps there that you want to ask about? Any step there that, this will definitely be on the test, so we want to make sure that you understand each of those steps. Ugh, really? I'm going with this way. That looks a little more sanitary. All good? Any algebra demons haunting you? You should exercise them now if you have a question. There's no dumb algebra question because algebra is dumb. So if there's any step that you're not sure about, let's talk about it. Everyone follow the derivative thing? So the derivative of a log is 1 over the inside, the reciprocal of the inside. So you just put 1, and then whatever the inside is, put it under the 1. And the derivative of the inside, derivative of 1 is 0, derivative of this fraction, use the power rule. Yes?
Why do we want to make it infinity over infinity? What?
Infinity over infinity or 0 over 0,
So
because we want to use L'Hopital's rule. when you have an indeterminate form of this type, what you do is create something that is you either push the infinity to the denominator or you push the 0 to the denominator, and you can create one of those two forms. Once you have one of these two forms, then you can use L'Hopital. So we can't use L'Hopital until we have infinity over infinity or 0 over 0. It's got to be one of those two. We can't use L'Hopital directly when it's 0 times infinity.
Right. Because it's 0 times infinity.
So if you think about 0 times infinity, this isn't real math, but you could do this, right? If you push the infinity into the denominator, it's that. And 1 divided by infinity is 0. Or you could push the 0 into the denominator. This is going to look really awful, but we could do that. 1 over 0. Don't take a picture of that and say that I wrote that. So, but that's the idea. The idea is that if you push this into the denominator, you're taking the reciprocal of it, and the reciprocal of it will then go to infinity. If you take the reciprocal of infinity, that will go to 0. Okay, so let's talk about some terminology with sequences. The terminology here is pretty intuitive for the first one and the third one. So a sequence is just a list of numbers. It's an ordered list, it's not jumbled. We have a specific value for the first position, the second position, the third position, etc. So it's ordered. You can't just mix them up. There are a bunch of weird theorems about rearranging terms of a sequence, but that's not what we are dealing with here. So we have this specific list of numbers. And we'll call that list of numbers, that sequence, increasing if the values are going up. If we look at the sequence with the black dots, that would be an increasing sequence. The dots are going up. Third one, it's decreasing. Terms are going down. And then we've got these two oddball ones, which are annoying. Mathematicians love to be as general as possible, no matter how impractical it is. So let's talk about what they mean, and then I'll talk about what I mean by being impractical. So non-decreasing, it is what it says. It's not decreasing. So if a sequence is not decreasing, it's either staying the same or going up. So it's flat or going up. That's non-decreasing. It's not increasing because there's some flat spots. Right? So if there's some flat spots, it's not increasing. So non-decreasing means it stays flat or it goes up. It trends up. But there are some flat spots. Non-increasing means what it says. It's not increasing. So if it's not increasing, it's flat or trending down. Flat or trending down. Now, in practice, can any of you think of a function that is truly non-decreasing or non-increasing that's not just increasing or decreasing? Can you think of one?
X cubed?
No.
No?
That's increasing. There's no flat spots.
It's not like...
It's flat-ish. It's flat-ish, but there's never 2 points on the same horizontal line.
Oh, 2 points.
Right? For it to be flat, there would have to be at least a pair of points on the same horizontal. The only normal way to come up with a function that's truly non-decreasing is to do it with a piecewise defined function. So you could define a piece of it to be flat, and then a piece of it to go up, and then a piece of it to go flat. So you could define, something like this with a piecewise defined function. So this right here would be non-decreasing. So in other words, to create a function that's really non-decreasing or non-increasing, you really need to be dealing with piecewise defined functions. And we are not dealing with piecewise defined functions 99.5% of the time. We're dealing with, f of x equals some function, a ratio, an exponential, power function, something, right? So it's just impractical. When you see the word non-decreasing in any of our homework or any problems that we are dealing with, you can just think of that as increasing. If it's non-decreasing, just think of it as increasing. If it's non-increasing, just think of it as decreasing, and it will work every single time in this class. The only time that you're going to need that level of nuance is when you get way further up in math or engineering and you're dealing with maybe step functions, but those are defined usually in a piecewise manner. So just remember that they are what they say. Non-increasing means it's not going up. Non-decreasing, not going down. So this one is flat or up. This one is flat or down. Monotonic means that it's not oscillating. I think that's the most intuitive way to think about monotonic, is that it's not oscillating. So it's not doing like a sine or cosine type of thing. It's not going up and then down, any kind of movement like that. So it's either non-increasing or non-decreasing. It's, if anything, it's moving in one direction. It never comes back down if it's going up. If it starts up, it can't come back down. So that'll be monotonic. It's trending up or it's trending down. And again, it's just absolutely fine to replace this with decreasing and increasing. Totally fine. That's what we are going to see in practice. And then we've got a couple of bounded options. So a sequence is bounded above if there's a ceiling. If the sequence never goes above a certain y value, then it's bounded above. If it never goes below a certain y value, it's bounded below. So bounded above, there's a ceiling. Bounded below, there's a floor. So when we look right here, it appears that this red sequence is bounded below by y equals 1. It appears, and again, graphs can be very misleading, but according to this graph, it appears that the red sequence is bounded below by 1, and it appears that the black sequence is bounded above by 1. Does that make sense? Now, the red sequence is also bounded above, right? All these red dots right here, assuming that it's doing what it's trending, or what it looks like it's doing, and doesn't like rocket up all of a sudden. This is also bounded above by a 2. And the black sequence is bounded below by 1/2. So this red sequence here is, oh, down, oh, I didn't even see that. Thank you, 0. Yes, yes, bounded below by 0. That point counts. Now, when someone says a sequence is bounded above, there is an infinite number of upper bounds if there is one. Right? The 2 acts as an upper bound, so does 3 and 4 and pi and e, all these horizontal lines you can imagine up here. So if a function is bounded above, there's an infinite number of possible upper bounds. The one that's the most interesting is the lub, the least upper bound, the one that's closest to the sequence. If you have an upper bound, the one that's the most important is the least of all those upper bounds, right? And so if we look at this black sequence here, okay, this is an upper bound for that black sequence. Not very helpful, though. It's not the limit of the sequence. The limit of the sequence appears to be 1, so that's the least of all the possible upper bounds. That's the one we're most interested in. And similarly, if we have a bunch of lower bounds, like if we think about this red sequence, 1 is a lower bound, according to what we see, but then also 1/2 is a lower bound, 0 is a lower bound. It would be the greatest of all the possible lower bounds that's going to be the most interesting. But we don't really care about that terminology in here, just so that you kind of get the idea that if there is an upper bound, there's an infinite number of them. If there's a lower bound, there's an infinite number of them. The greatest lower bound and the least upper bound are the two that are most important. So both of these sequences appear to be monotonic. Right? This is just decreasing, and this is increasing. So we would think of those as monotonic. And those are the pictures. Right? So this decreasing sequence is also non-increasing. It's not going up. But if we stick to decreasing and increasing, that's going to be sufficient for us. That extra nuance we don't need. All right, let's take a look at the most important sequence of them all, the geometric sequence. Most important sequence by far. Why? Well, the first reason that it's so important is that it's a super common type of thing that we will see in nature where things behave geometrically. Second is that you can actually find the sum of a geometric series. So if we have a geometric sequence, a geometric series is just what we get when we add all those terms together, and it's one of the two. There are only two series that we will look at that we can actually find the sum of. So a geometric series is practical, and you can find the sum of it. So that's why it's going to be so important. So a geometric series, let me just write one on the board so you have a sense. I'll just expand this one here. So I'll write a geometric sequence here. So a geometric sequence, we have a common multiplier. So in this case, I think it's fairly obvious what the common multiplier is. So this is a geometric sequence. And what is the common multiplier in this case? 1/2. Yeah, so 1/2 is the multiplier that takes us from one term to the next. Repeated multiplication by 1/2. And it would be called a geometric series if we added all those terms from a geometric sequence, if we added them all together. That would be a geometric series. So we know about the behavior of geometric series already. So a geometric series has this form of r to the n. So a sub n will be r to the n. R is that common ratio. And this particular geometric sequence starts, well, it has an r value of 1/2, and it has an n value that starts at 1. Because this sequence here is going to start at the first y value, or the first sequence value is 1/2. It's there. So the n values down here are these. Those are the n values. So a sub n is r to the n. It's 1/2 to the 1, 1/2 to the 2, 1/2 to the 3, 1/2 to the 4. All right. And we already know that if we take a number that's less than 1 and we do repeated multiplication, we know it's going to go to 0. 1/2 times 1/2 is a fourth. Fourth times a half is an eighth. Those are going to 0. So we know that we are going to have convergence when we have an r value less than 1. The limit is going to be 0. If the r value happens to be 1, that means our sequence is really 1, 1, 1, 1. If we're continually multiplying by 1, the r value would be 1. So if we have this, that is kind of a uninteresting geometric sequence, but it's going to converge to 1. Right? That sequence converges to 1. So we will have convergence as long as the r value is less than or equal to 1. Now let's go to the negative numbers and think about the negative numbers. If the magnitude of these is less than 1, so if it's like -1/2, that's also going to converge to 0. If we think about -1/2, we multiply by -1/2, we get +1/4. Multiply by -1/2, we'll get -1/8. And it's pretty obvious that this is trending to 0. So this is also going to converge to 0. But what about -1? So if we have -1 here, so if we start with a +1, let's suppose, actually we're going to start with -1 because we've decided that the first n value is 1. So if our ratio is -1, -1 to the 1 is -1. So this would be our sequence with that's a geometric sequence with an r value of -1. Does that converge? Converge or diverge? Diverge. Converge is only when the terms in the sequence are getting arbitrarily close to a single number. Those are not getting arbitrarily close to a single number. They're bouncing around. So all we can say is that this limit does not exist. So we would write that. Does not exist. So sequences either converge or diverge. We just figured out that a geometric sequence will converge if r is between -1 and 1, including the 1, excluding the -1. Otherwise, it diverges. So the interval for a geometric series is right in the middle, -1 to 1 for a geometric sequence. And it will turn out that a geometric series has a very similar region of convergence, with one exception. Let's just talk about that one exception for a moment. If this is our geometric sequence, if we add all those ones together, do we get convergence for the series? No. If you add 1 plus 1 plus 1 plus 1 plus 1, that sum is going to go to infinity. So for a geometric series, the convergence will be -1 to 1, excluding both endpoints. But for a sequence, it does converge. So here are some pictures of these geometric sequences. We can always think of a sequence as a subset of a continuous curve. So the continuous curve is 0.5 to the x. It's that exponential decrease right there. Here we have exponential decrease, but we throw in a switch. So the terms are going to oscillate around 0, but they will approach 0. 1.1 to the x, that's our continuous curve right there. And the sequence that's embedded in it will have 1.1 and then 1.1 times 1.1, 1.1 raised to the 3, 1.1 raised to the 4. Clearly, that's going to diverge. We've taken a number bigger than 1 and multiplied it by itself. That'll diverge. If we take our same ratio except put a negative in front of it, so negative 1.1. So I drew it as 1.1 to the x, but if we throw in a switch, then the red dots are oscillating. Clearly, that limit doesn't exist. It won't exist. You can't say that it goes to infinity, but it's going to oscillate. It won't exist because the terms aren't going to a single number. So pictures of some of these sequences. If a sequence is oscillating, it's not increasing or decreasing. And if it's oscillating, it's going up and down. It's not going to increase or decrease. So it is not monotonic. In calculus, you had a squeeze theorem. You had a squeeze theorem for functions in calculus when you took limits. The idea here is the same. Sequences are functions. They're functions with a domain of the positive integers. So all this theorem is saying is that if we've got these two sequences on the upside and the downside, so A sub n is down here, it's the red ones, and then the B sub n, which one's the B? The C sub n is on the top, and then the B sub n is sandwiched in between, if it's in between, and both the upper sequence and the lower sequence, if they both converge to L, then the one in the middle has to converge to L also. Very intuitive. Right? There's no way for it to get outside if it's always in between the two. It has to converge to the same limit. So let's look at a couple of these. Now, for the squeeze theorem to work, you need to know a fact. You need to know a bounding fact for whatever the function is within. And both of those functions, inverse tangent and cosine, we know a bounding fact. We know that inverse tangent of n is always less than pi over 2 and always greater than negative pi over 2. So the only way the squeeze theorem is going to work is if we have some sort of bounding fact that we can apply to the function that's in there. And then all we do is take our inequality and multiply it or divide it by something to try to match what's inside the curly brackets, to match the a sub n. So what do? Divide by n. So we divide both the left and right by n. We divide the center by n. Oops, divided by n. So then once we've done that, we've matched the inside. So now what we do is take the limit. So we're going to take the limit of all three parts. Take the limit as n goes to infinity of each of these. And what is going to be the limit of the left and the limit of the right?
0.
It will be 0. And maybe what I'll do is put an equal to here also. So certainly it's less than, but it's also true that it's less than or equal to. And I'm just doing that because if this goes to 0 and this goes to 0, it's a little funny to say 0 is less than the limit of this, and that's also less than 0. It just doesn't match exactly. We can put the equal to sign in there because it's true, and that's going to give us a better match in the end with the notation. So we will have in the end that the limit of this function, the limit of a sub n, is sandwiched between 0 and 0, so its limit must also be 0. So therefore, the limit of arctan of n over n must equal 0. So the only way this squeeze theorem works is if you have some sort of bounding information on the function inside there. Let's do one with cosine. What's cosine bounded by? Yeah, -1 and 1. So we're going to start out this way. We're going to say, all right, well, if we have -1, we have cosine. Right? Those are our bounding facts. We already know that cosine is always less than or equal to 1. It's always greater than or equal to -1. And then we just sort of go through the motions here. It's not that complex. We're just trying to match the inside. This is much more about notation than it is about concept, really. And so then we take the limit of all three parts as n is going to infinity. And when we take the limit of the left and the right, in both cases, those limits are going to be equal to 0. And that allows us to draw our conclusion that therefore the limit of cosine of n over n as n goes to infinity is going to be 0. Let's think about this cosine. Let's think about the result here for a moment, because there is an important concept here. If we were asked to find this is how we formally prove that the limit is 0. But let's think about what's happening in here. When we go inside, we see a fraction where the denominator is growing without bound, and the numerator is not constant, but it is bounded, right? The numerator is fixed. It can only be wobbling around between -1 and 1. And if the denominator is growing without bound, that little wobbling around between -1 and 1 is going to be insignificant. So in the long run, we will be just sort of writing the limit of this as 0 without going through all the motions here. The supporting math is the squeeze theorem is what allows us to do it. But in practice, as we go forward, when we see something like this, that's what we're going to say to ourselves. If the numerator is constant, certainly, if we have something like the limit of 1 over n, certainly we can just jump to the answer being 0. And now we're saying, well, if you have a numerator that's not a constant, but that numerator happens to be bounded, if we put a sign of n here, we're going to say, OK, we get the squeeze theorem. We get that it's going to behave as if the numerator was a constant, if that numerator is a bounded function. So in the long run, we're not going to go through all this supporting math, but that is why we can go from here to here immediately. Because the denominator is growing without bound. And the numerator is trapped. Question?
Would it work the same way with tangent?
Well, tangent is not bounded.
It goes up, but it's bounded on the sides.
So,
Like X and
so when we say function is bounded, we mean the function values are bounded. So so we're talking about horizontal or horizontal lines.
yeah.
So it's trapped in between a ceiling and a floor if it's bounded. So when we look at the tangent function that has that looks like this, it's true those are horizontal bounds, but that's different than the function being bounded. If the function is being bounded, we mean that. Right, this is more the domain being bounded.
Okay, so
Right here, the domain is going from whatever interval we're looking at, negative pi over 2 to pi over 2. But the function is the vertical travel. So that's not that's an unbounded function. Little theorem here. If we have a bounded monotonic sequence, it must converge. So if we have, and again, let's think for monotonic, just think increasing or decreasing. Don't bother with the non-increasing, non-decreasing business. So we have an increasing sequence. If it is bounded above, that increasing sequence must have a limit. There's nowhere for it to go. If it's bounded above and it's increasing, right, it can't pass through whatever the least upper bound is. So a bounded monotonic sequence has to converge. So an increasing sequence that's bounded above will converge, and a decreasing sequence that's bounded below has to converge. No choice. There's nowhere for it to hide. Right? If it's decreasing, it's got to get closer and closer and closer to this greatest lower bound. Has to have a limit. So must have a limit. If it's a bounded monotonic sequence, it has to have a limit. That makes sense? Question?
She was just asking about the bound, they both have bounds.
Right, so if we look at this increasing sequence here and we're told that it's bounded, that means that there's going to be a ceiling that it can't pass through, which forces it to have a limit. If it's increasing so it can't dip back down, if it's increasing, it has to be trapped by that lowest ceiling, and that's going to be the limit of the sequence. So the least of all the upper bounds is the limit of the sequence. The greatest of the lower bounds is the limit of the sequence.
So
Mhm.
non-decreasing bounded below.
So non-decreasing, bounded above.
Well, below would not have a limit, right?
So when we say a limit, we mean a limit at infinity.
Right.
So as we are going to infinity, this is increasing, so it's bounded above, so it's got a limit that's one of the upper bounds.
Okay.
So we're not. So it's true that this is bounded below, but an increasing sequence bounded below doesn't necessarily converge. Do you agree with that? An increasing sequence that's bounded below that. Like here's a picture of an increasing sequence, and it's bounded below because it started right there. All right, there's a lower bound. That doesn't mean that it's going to converge. Right? It's not going to have a limit. So if it's increasing and bounded above, or decreasing and bounded below, but we can't mix and match them. We can't say that a decreasing sequence that's bounded above converges. Right? Here's a decreasing sequence bounded above. It's not going to converge. So it's got to be increasing. So here, instead of non-decreasing, we can say increasing. So if it's increasing and bounded above, it will converge. Or if it's decreasing and bounded below, it will converge. That make sense? So if it's going down and there's a floor, it has to converge. If it's going up and there's a ceiling, it has to converge. There are times where we have functions that we cannot take limits of. Like we have all of these techniques. And many times we are going to be dealing with functions where we have this kind of thing, infinity over infinity, or maybe 0 over 0. And we have strategies for those. We have L'Hopital's rules, a primary strategy for that, right? If we have one of those indeterminate forms. It's a primary strategy. There are other strategies. You saw some in Calc 1 where if you can factor the top and bottom and cancel out a common factor, there are other strategies. In calculus, usually we're doing this kind of thing with L'Hopital's rule. Sometimes you divide by the highest power in the denominator. So there are other techniques. But there are some functions we cannot differentiate. So we are going to see functions that are oddball functions, like the factorial function. The factorial function, we do not know how to take the derivative of the factorial function. The factorial function is repeated multiplication. So for example, just to make sure if you haven't had statistics, maybe you haven't seen the factorial function. So the factorial function is repeated multiplication down to 1 for a positive integer. So that is 5 factorial. 10 factorial, 10 times 9 times 8, 2 times 1. Right? Factorial is just repeated multiplication by integers down to 1. So at this moment, factorial for us is only defined for positive non-negative integers. 0 factorial is defined to be 1. So 0 factorial is 1. But at this moment, when you think about factorials, you should be thinking about non-negative integers. So 4 factorial, 4 times 3 times 2 times 1. Pi factorial, not yet. But you can do a pi factorial. You just can't interpret it the same way. You can do a pi factorial, though. There is a very cool function called the gamma function. The gamma function is the generalization of the factorial function, and it creates factorial values for non-integers. If you look up the gamma function. So it matches for all the integers, but then it creates this continuous function in between. So 4.5 factorial will be in between 4 factorial and 5 factorial. So it creates this funky function that is a generalization of factorial. Okay, so factorial function. We also have a power tower. So a power tower is where you have x to the x, or n to the n, or n to the n to the n, or x to the x to the x, whatever. Power towers, we do not have a way to find, we can't take the derivative of that function either. So if there are functions that we cannot take the derivative of, sometimes, if we can't do the math, sometimes we have to just say by growth rates. We just have to know the following. So this chart tells us the speed at which a function grows as n is going to infinity. So the function that we will see in this class that grows the fastest is the power tower. So the power tower is going to grow faster than any of the other functions we see. The next quickest function is the factorial function. So that's what these little double inequality symbols mean. It means that this one grows faster than that one grows faster than that one, etc. This one, that's our exponential function. So we have a power tower. That's the quickest. And then we have factorial. And then we have exponential. And now here, they make it more complicated than we need to have it. We can kind of just ignore, let me use a lighter thing so you can read it if you want to. We can kind of ignore those. These are the same, essentially, as this one. This one is a polynomial. So right here, it's just a polynomial with an exponent that's, what they're saying here is that, like, if you have n to the 5, it's going to grow faster than n to the 2. That's what they're trying to imply there. But we don't, comparing polynomials is simple. If you have x to the 5 over x to the 3, you cancel the common factors and you end up with x to the 2. So you don't really need to even think about that. That just comes out in the wash. So what's important is that an exponential is going to grow faster than a polynomial. And then the same idea down here, they've got these log raised to the q power. Doesn't really matter. This is just a log function. So logs are going to grow to infinity the slowest, and then polynomials, and then exponentials, and factorials, and then power towers. So these 5 are the ones that we really need to focus on. Natural log the slowest, power tower the fastest. So when we look at something like this, we have no way to take the derivative of top and bottom. Right? Both go to infinity, but what we do know according to the growth rate fact right here is that the denominator is growing faster than the numerator. So a power tower goes to infinity faster than a factorial. So what do you think that limit's going to be? 0. So all we can say when we have things that we can't do math on, we say by growth rates. That's all we can say. So all these growth rate things can be proven with math that we can't do at this stage. So we just have to know that power towers grow the fastest. So this one right here, we have n to the 1,000. So that's a polynomial over an exponential. Polynomial over exponential. This one, you could use L'Hopital's rule. But how many times would you have to use L'Hopital's rule? 1,000 times to get that numerator. Eventually, a polynomial, if you differentiate it enough, eventually it goes to 0, right? If you have x to the 4th, you take the derivative, you get a cubic. You take the derivative, you get a square. You take the derivative, you get a linear. You take the derivative, you get a constant. Take the derivative of the constant, you get 0. Eventually, repeated derivatives of a polynomial will give you 0. But who wants to do L'Hopital's rule 1,000 times? No one. So this we would think of as a polynomial divided by an exponential. The exponential is going to go to infinity faster than any polynomial. Maybe not in the first million terms, but if you go out 10 million terms, any exponential is going to blast past a polynomial, no matter how high the power on the polynomial is. If it's n to the 10 million, 2 to the n will eventually pass it, and pass it fast. It might be way, 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 way out there, but eventually it will do it. And so here, the denominator is growing to infinity faster than the numerator. So once again, we're going to have a limit of 0 in this case. But we can't do the math. So we only do this growth rate thing when we can't do the math, when we can't take derivatives. All right, any questions on those concepts? So we just have to have those 5 functions in the order. Most of them you're already familiar with. You know that polys grow faster than logs and exponentials grow faster than polynomials. These are the 2 new ones, perhaps. So factorial and power tower. Power tower grows the fastest. Okay. Now, I don't know what Calc 1 you took. Some Calc 1 classes you do epsilons and deltas. Some you don't. It's kind of the formal way to define a limit. We are not going to get into the formal definition, or we're not going to ask you to do the formal definition, but we need to at least talk on it so you get the concept. So the idea for a limit to exist is that when you go far out in the sequence, the terms are arbitrarily close to some constant value. Usually we call it L. So here, L is the limit of this sequence. So if we could draw a horizontal, if we could draw a straight line there, that was dashed. That is what the limit of this sequence is. And so in order to talk formally about limits, this is what we say. And you should interpret this as the difference between the sequence value and the limit. So you can imagine it's just the distance between the point and if the limit is going to be this blue line L, right there is just distance. It's the distance between the sequence value and the prospective limit. And so all this says is that no matter what you pick for that epsilon, so that epsilon creates a little tunnel. And it says that no matter what you pick for that epsilon, it could be 0.1, could be 0.01, could be 0.00001, doesn't matter. What it says is that eventually the sequence has to be in that little tube, eventually. Then the limit is going to exist. If no matter how small you draw this little epsilon interval, this little tube, if you can go far enough out so that the rest of the sequence is within that, no matter how small you ratchet it down, then the limit is going to exist and be L. All right, so the limit won't exist if this is not true. And it's kind of a strange concept because it says for every epsilon, so it says no matter what you pick for epsilon, so epsilon's just bigger than 0, eventually you're going to have a tail in the tube. If you create that little epsilon tube, if the limit exists, you have to go out far enough, the tail from there on out will be inside that little epsilon tube. So that's what it means for the limit to exist, that no matter how small you draw that epsilon tube, the tail of the sequence is in the tube, no matter what. That's what it means for the limit to exist, that you can ratchet it down. We're not going to formally do that. Sometimes in Calc 1, you say, OK, we'll find the epsilon and find the delta and do these things. We just want the concept that the tail has to be arbitrarily close to L if the limit is going to be L. And that's what we mean by arbitrarily close, a tiny, 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 tiny number. All right, let's go ahead and take our break now because we're going to start a whole new type of sequence. Let's just take our break before we talk about something new. Go look outside at the cold weather.
Yeah, I think we're supposed to look at the...
Recurrence relations. So these are harder to analyze. If we have a sequence that's given to us explicitly, all we have to do is take the limit of a sub n. We use L'Hopital's rule, we do whatever we need to do, and we get the limit. Recurrence relations are a little different. And there's a clever technique. If we are reasonably assured that the limit does exist, there's a clever technique to find that limit. But this technique only works if you know that the limit is going to exist, or you're reasonably assured. So when we look at this recurrence relation, so we've got that a sub n plus 1 is that, and we're starting at a sub 0 is 2. So I did a couple of iterations in Desmos. So we start at 2, and then we take the 2 and we plug it back in. So we're going to get 2 plus 1, which is 3. So we get 3/2 for our second value. And then we take the 3/2, we plug it back in, and we get the next value, which is 1.416 repeating. And then we take that one and plug it back in. So I just did a copy-paste in Desmos to try to get these values. And if we were to continue on, can you see that it looks like these values are trending towards 1.4 something? Like right now, here we have 1.416, blah, blah. Now we have 1.4142. So the difference is getting tinier and tinier as we go further out. And if we were to do a couple more, it feels, or if we were to graph this, it feels like we probably are converging to 1.4 something. So if we're reasonably assured that this sequence does converge, we can do the following thing. So first off, a sub n plus 1 and a sub n, those are the same sequence except for the very first term. But this, n is starting at 0. So if n starts at 0, this one right here, let's put them on different lines. This one, if n is starting at 0, this sequence right here is a sub 0, comma a sub 1, etc. This sequence, if n is starting at 0, is a sub 1, comma, a sub 2, comma, etc. So they're the same, except that this sequence has one extra term. Point being, they have the same limit. A sub n plus 1, if you consider it a sequence all by itself, it has the same limit as the sequence a sub n. So what we're going to do is this crazy thing. We are going to take the limit of both sides of this equation. We're going to take the limit of the left side as n goes to infinity, and we're going to take the limit of the right side as n goes to infinity. So we're taking the limit of the entire equation. And we are going to assume that the limit is L. We are going to assume, this is our assumption, we're going to assume that both of these, if they converge to the same thing. And based on our empirical evidence here, we're thinking, okay, it looks like there's going to be a limit. So we're going to say that those things converge to L. So if we take the limit of both sides of that equation, here's what we end up with. We end up with this sneaky little algebra equation. If the limit of a sub n and the limit of a sub n plus 1, if that's L, all right, we distribute the limit. We push the limit inside. That's what we get. So if we can solve that algebra equation for L, that is going to give us the limit of the sequence if the limit does exist. So the one thing about this is that there's no, like this is not a guarantee, looking at this, that the limit exists. That would take some more complicated math. So I'm going to multiply both sides by 2. We want to get all the L's on one side, so I'm going to subtract an L. So we get that. Multiply both sides by L. That's going to give us L squared equals 2. So L is going to be the square root of 2. I know it can't be negative square root of 2 because these are all positive numbers. There's no way to create a negative here. We're not subtracting. So what this says is that the limit of this sequence, assuming it exists, is square root of 2. So it's a pretty clever technique that works when you are assured that you're reasonably assured that your sequence does in fact converge. Let me just show you another one though. So let's suppose we have a sub n plus 1 equals a sub n plus 1. Let's suppose we have that sequence. And let's suppose it starts at a sub 0 equals 0. So this sequence, do you think this sequence converges? Let's see. We start with 0. What's the next term? 1. We plug 0 in here. 0 plus 1 is 1. What's the next term? 2. Plug it back in. 3. So clearly, this sequence diverges. That sequence diverges to infinity. But notice that if we were to take the limit of both sides here, there's nothing that stops us from taking the limit of both sides here. There's nothing that stops us. But there's only sometimes that it makes sense. That limit is only going to make sense if the sequence actually converges. But we could still do this. We could say, oh, this is equal to, oh, this is a bad one though, because we end up with 0 equals 1. So that actually kind of gives us a clue that this doesn't exist. Let's see if we can modify it a little bit so that we actually get a number. I didn't think about this too carefully ahead of time. Let's do this. Let's change it. So here, 0 equals 1, we know that's false, so that's a strong indication that the sequence doesn't converge after all. But we can get bunk answers here that are meaningless. Let's see if we can create one. Let's make this that. Let's make it a square. And let's start with a sub 0 equals 2. Let's see what happens here. So a sub 0 is 2. Plug it in there, we get 4. Plug 4 in there, we get 16. Plug 16 in there, we get 256. And I'm going to put the dots now because I can't do the rest of those. So, okay. So clearly that goes to infinity. Let's see what happens over here. So if we take the limit of both sides, we're going to get L equals L squared. And if we subtract, we're going to get L squared minus L. We're going to factor L times L minus 1. So this tells us that L is equal to 0 or 1. Certainly we know it can't be 0 because all the numbers are positive. So this technique is telling us that the limit of that sequence, if it exists, is 1. Obviously, the limit of that sequence doesn't exist. So obviously, that 1 is meaningless in terms of taking the limit of a sequence. So we just have to be a little careful. When we use this technique, it's only valid. You can do it anytime you want, but it's only going to give you something that is meaningful if you're reasonably assured that the sequence converges. And this is how, I'm sure you've seen the physics thing. If you add all the positive integers together, you get negative 1/12. Have you guys seen that? No? Oh. If you look in our D2L shell, it's one of the videos in there is that video. And they do some stupid proof that you add up the positive integers and you get negative 1/12. String theory people use these weird results. Obviously, if you add 1 plus 2 plus 3 plus 4, in the math sense, that cannot converge to negative 1/12 in the math sense. So they do some funny things that are not mathematically sound to come up with that. And it's not to mean that just like here, maybe that 1 has some relevance to this sequence in some way that we don't understand at this time. Just like that negative 1/12. It's not the sum of the positive integers in the math sense, but maybe it has some meaning that they ascribe to it. Some physicists ascribe meaning to it in some like 12-dimensional or 13-dimensional space. Maybe it has some meaning, but in math, that diverges, and that 1 is not the limit of that sequence. All right. Okay, so that technique is cool if you're reasonably assured that your sequence converges. So let's try one more here. So see if you all can figure out what this sequence converges to. So it certainly appears empirically that, okay, we're getting tighter and tighter and tighter to 2. So it feels like it probably converges to 2. So let's see what you come up with if you use this technique on this recursive sequence. If you're stuck on any step there, the strategy is to take the limit of both sides of that equation. When you take the limit of both sides of that equation, remember that the square root function is a continuous function. So that means you can shove that limit right inside the square root. Right? Limits can pass through continuous functions, pass right into them. So the limit of that square root is the square root of the limit. Move it inside. Getting there, right? Okay, so the strategy is to take the limit of both sides. So we're going to take the limit of a sub n plus 1 equals the limit of square root 2 plus a sub n. So when we're dealing with sequences and series, the limit is always as n goes to infinity. So on the left, we have L equals, and on the right, we have square root of 2 plus L. So the limit symbol can jump right inside the square root because the square root is continuous. We square both sides. We move everything to one side. So we'll have L squared minus L minus 2 equals 0. We factor it. We get L minus 2 and L plus 1. So this tells us that there are two possible answers, -1 or 2. The values of this sequence are never negative, so we rule out -1, and this shows us that the limit is in fact 2. So if the sequence does converge, this will find the limit. Clever little algebra technique. Just looking at this one reminds me of another kind of cool high school type problem that they probably don't cover anymore. Anyone know how to deal with this type of thing? If you have an infinitely nested square root, that is equal to an integer. You start typing in your calculator, you can, you don't have to go out too far and you'll be able to figure out what integer it's equal to. So this again is an algebra thing. If we just let it be x, what do you think we'll do to both sides? Anytime you're trying to solve a square root equation, don't you square both sides? So then we have that. And then that square root business is just x. So this is going to be 6 minus x equals x squared. So then we have x squared plus x minus 6 is equal to 0, moving everything to one side and factoring. So we're going to factor that into x plus 3 and x minus 2 to 0. So then x has to equal -3 or 2. But this is a positive square root, so it definitely can't be equal to -3. So that is equal to the integer 2. So the next time you're writing a check, I know how you all write checks these days. I dare you to write that on there for a $2 check. Wouldn't you love to see the reaction? Some rando looking at a check with all those squares. That'd be funny. All right. Okay, so algebra has usefulness. All right, let's go to 10.3, talk about infinite series. All right. So we had to do all this sequence background stuff because the way we analyze an infinite series, which is way more important, is to use that sequence stuff as a tool. Infinite series are the things that are much more relevant to math and science than just plain old sequences. But the way we analyze them is through sequences. So remember, we talked about this on Monday, or Tuesday. I talked about it on Monday also. So a sub n, that is the sequence of terms. So these are the terms that we are going to add together. So sequence of terms, that creates our series. The series is the sum of the sequence of terms. Then we create our sequence of partial sums. The sequence of partial sums is what is going to be analyzed. So in your mind, this is what you should be thinking of when you are thinking of your sequence of terms. Your sequence of terms must be going to 0 if you are going to have convergence. So this is what you should have in your mind for your sequence of terms. So there's your a sub n. That's the visualization you should have, just as, the whoop, down to 0, down to the x-axis. the partial sums, the image that you should have in your mind for the sequence of partial sums, for a convergent series, so if our series is converging, this point up here has got to match, but then you're adding subsequent values, and if it does converge, this one you can't make dashed lines for some silly reason. So this is what you should be visualizing for your S sub n's for a convergent series, and L will be the limit of that sequence. So the A sub n's need to be going down to 0. The S sub n's should be forming an increasing bounded above sequence. So if we have a convergent series and there's all positive numbers, everything's positive, these are the images you should have in your mind. A sub n's go to 0, S sub n's go to the limit of the sequence of partial sums. And then L, if L exists, then we say that this series is equal to L. L is the sum of the series. So remember that your S's, S sub 1 and A sub 1 are the same, and then S sub 2 is the sum of the first two, S sub 3 is the sum of the first three, S sub 4 is the sum of the first four, S sub n is the sum of the first n. So if the sequence of partial sums converges to L, then the series equals L. The value of the series is L. So that's our background. That's what we need in the background to understand series. We need to have that terminology and those ideas solid. Any questions on why the A sub n's look like that, why the S sub n's look like that, or how we build the S sub n's? So that stuff has to be solid before we get going. Mm-hmm.
So why are they always like that?
If the series converges, this is the pattern. If the series diverges, then things are different. If the series diverges, you still will have the A sub n's going to 0. If the A sub n's don't go to 0, you know it diverges. You can't add a positive number to itself repeatedly and get something finite. So if the A sub n's don't go to 0, immediately you know there's divergence. But the terms could go to 0, just not 0 fast enough, and then the partial sums will go to infinity. So this is the case we're most interested in, where the terms go to 0 fast enough that we have convergence for our partial sums. That's the case we're most interested in. So that's what it would look like in all cases where we have positive A sub n's and we have convergence. So the convergence of the sequence of partial sums is always going to be this increasing sequence with an upper bound. And a bounded increasing sequence will converge. So our most famous series of them all, geometric series. So we saw the geometric sequence earlier. Notice the only difference is that for a geometric series, convergence does not happen at 1. The sequence 1, 1, 1 does not, if you turn it into a series, 1 plus 1 plus 1 does not converge. So we take that away. So our convergence is strictly in between -1 and +1 for a geometric series. Otherwise, it diverges. Now, I said earlier that we can find S sub n for a geometric series. So that's what we're going to do. And they've told us up here, look, right here. This says if we have an infinite geometric series, its value is A divided by 1 minus R. That is the value of the infinite series. So for a geometric series, A represents the very first term. Let's expand it just so, it's right here. So A is the very first term. R to the 0, of course, is 1. So A is the first term in the series. That's what A always will mean for a geometric series, the very first term. If your series has an index that starts at 0, you plug it in, and whatever you get for that first value, that is your A. If your series starts at 10, You plug in the 10 for the k, that's going to be your first term. No matter what, a is the first term, regardless of where the index starts. A means the first term in the series, always. R is the common ratio. So we're going to do repeated multiplication by R. That is our common ratio. That's going to take us from one term to the next. And that's all we need to know to find the sum of an infinite geometric series. A over 1 minus R. That's it. Not too hard. Let's prove that that's the case. I mean, it's shocking that the sum of this infinite series, all you need to know are those two numbers, and you get the sum of the whole series. Okay, so let's prove that that's true. So this S sub n is the sum of the first n terms. Okay, sum of the first n terms. If you were counting beginning at 1, the index would go from 1 to n. But for a geometric series, the counter starts at 0. So the n and the k don't necessarily align. This is the first term, this is the second term, this is the third term. So if we are going to start our counter at 0 and we want n terms, we're going to end it at n minus 1 up here. All right, so, or if we're plugging in the k, we're going to have to go all the way up to where k goes 0, 1, 2, up to n minus 1. So the k value and the term number don't always align. Does everyone follow that? So if we have 5, 1, 2, 3, 4, 5, but if we count starting with 0, 0, 1, 2, 3, 4, right? We're shifting everything to the left by 1. So if we're counting 1 to n, we have 1 in n, but if we shift it all to the left, it's going to be 0 to n minus 1. So that's what this is representing. So S sub n, regardless of your k, S sub n is always the sum of the first n terms. Okay? So there we have it. S sub n, we're going to go all the way out like that. Now we're going to multiply both sides by r. So right here, we've just multiplied by r, so this is r times S sub n. And what we're going to notice is that there's a whole bunch of cancellation if you subtract the two. If you take the first line right there, there's S sub n, and you subtract off that one. So AR minus AR is 0. AR squared minus AR squared is 0. AR cubed minus AR cubed is 0. The only terms that persist are that one and that one. All these others are canceling all the way down when you do the subtraction. Okay, and now we just have algebra. If we factor out the S sub n, what remains is a 1 minus r, and we divide it to the other side. There is our sum. This is the sum. This is the formula for S sub n. That's the formula for S sub n for any geometric series. So what we know is that the limit of a series, or the sum of a series, is the limit of S sub n. So L is going to be the limit of S sub n. So if we take the limit of this, and if r is less than 1 in magnitude, doesn't r to the n go to 0? R to the n is 0 as n goes to infinity if the absolute value of r is less than 1. So this part right here is going to 0 if r is less than 1 in magnitude. And that leaves a divided by 1 minus r. So that proves to us that no matter what, if you have a geometric series that is infinite, that is the sum of that series. And we proved that with just basic algebra. We started with our partial sum, we multiplied by r, we subtracted, we divided, and then we took the calculus part, we took the limit. All right, that's it. So that is This formula right here, super important. That is a formula that we all want to know. A over 1 minus R. So let's try it. So first, let's just talk a little bit about the indices, just to make sure that you're all on board with what we're saying with the indices and how they don't have to match the term number. So this is our partial sum. S sub n is going to equal that. And let's just look at a specific example. Let's pick the leading term, the first term, to be 1. So I'm going to replace the a with a 1. That gives us this. And let's say the common ratio is 2. Now 2 is bigger than 1, so we know that we're dealing with a divergent series. So that's okay. So we're going to replace the r's with the 2. So we know a and r. We end up with S sub n. There is our sum. Now, S sub 1 is always just the first term. S sub 2 is the sum of the first two terms. So there's S sub 2. S sub 3 is the sum of the first three terms. There's S sub 3. This formula here is another way to build those values. So when n is 1, we get 2 minus 1, which is 1. When n is 2, we get 4 minus 1, which is 3. But notice, the n's that we're plugging in there are the term number. So if I want the value of the second term, I'm plugging in a 2. But over here, k is starting at 0. So this term is from k equals 0. We'll put the k's up here. So the k values are 0, 1, 2. Put the n values down here, 1, 2, 3. So we just have to be careful. So the k value and the n value do not necessarily line up. They can, but they don't have to. All right, so down here when we're finding S sub 2, that's the sum of the first two terms. Plug in the 2 right there, we get the 3. So there's our sequence of partial sums. And clearly the limit of S sub n is infinity. So therefore we have divergence. This series diverges. But just be aware, k values and n values are different. Not always, but they can be. Okay, so there's a summary of it. Notice that in this case, when n is 1, k is 0. When n is 2, we have k equal to 0 and 1. So let's try some. Okay, this first one is a finite series. This is finite. So k is going from 4 to 12. How many terms are in this series?
13. Or no.
No, no.
8.
2 no's so far. 3 no's. I've heard 7 and 9. Those are better than 8. Which one is it?
9.
So let's do this. Let me show you, and then we'll come up with a way to confirm it. So what is the first term in this series? 2 to the 4. Let's just write it that way. Let's write it as 16. We can write that as 16. Okay, what is the next term in the series? What is our common ratio? Right, our common ratio is 2. So here are the terms in the series. And let's put our k value down below this time. So there's k equals, maybe I'll put the k as up top. Let me try to be consistent. So k up top, there's k equals 4, there's k equals 5, there's k equals 6. And we want to go, we'll do a short, this one's short enough that we can go all the way up. So we just keep multiplying by 2. 128, 256, 512, 1024. All right, let's see, where are we at so far with k's? So there's 7, there's 8, there's 9, there's 10. So then this is 2,048, and that's 4,096. All right, so how many terms are there? 9. So we do the upper minus the lower and add 1. That will always give us the number of terms if we have a finite series. So if we have a finite series, we'll do 12 minus 4 plus 1. That's going to be 9. Number of terms in the series. So it's kind of like the, if you have a fence, you've got fence posts, one fence right across the back wall. You have 2 columns right there, 2 posts at the end. There's always going to be one more post than the number of panels in between. Right, so we have to add that 1 to get to the last. If we have 5 panels, we need 6 posts. It's that kind of thing. We always need 1 extra for the end. So upper minus lower, add 1, that'll be it. Now, who the heck wants to add all those? No one. So all we have to do, though, is use our partial sum formula. So this is our partial sum formula. A is the first term, no matter what the K is, A always represents the first term. Doesn't matter what the K was to generate it. So 16 multiplied by 1 minus, common ratio is 2, n is 9 over 1 minus r. So that is going to be the sum of this series. So if we look in the denominator, 1 minus 2 is negative 1. If we distribute that into the numerator, we could just change the signs in the numerator. So that is the sum of our series. Hey Siri, what is 2 to the 9?
512.
So 511 times 16?
Didn't work on yours.
I know, I don't know why.
Your phone must have outsourced it.
I don't know why mine is not working. She can factor really well. Hey Siri, what are the prime factors of 7,425,256? She can factor so well. That's impressive. And then what's 512 times, or 511 times 16?
Hey Siri. What's 511 times 16?
There we go. All right. Yeah, it's good to have an assistant.
Yep.
So these are partial sums, finite sums, not infinite. These are harder than the infinite sums. Remember, the infinite sum formula is just a over 1 minus r. So we'll get to that in a minute. So let's go here. So we have a finite sum here. We have our formula up there. Let's identify the important things. What is n? N is the number of terms in this finite sum. How many terms do we have? 7 terms? Everyone agree? So if we started at 1, if it went from 1 to 6, then it's obvious, right? If it starts at 1 and goes to 6, then we know there's 6 terms. Right? But if it starts at 0, we would have to do that kind of shifting thing. So this one starts at 0. We added an extra term, 6 minus 0 plus 1, however you want to think of it. What is A? 1. So A is always the first term in the series. The first term is found by plugging in the initial index value. The index value starts at 0. And then what is the other thing we need to know? Common ratio. What's the common ratio? Pi. Now, if it's not 100% clear by looking at the summation notation, you can always do this. You can always start writing things out. It never hurts to write out the first few terms, or maybe all the terms, if there's not too many terms. And we're going to stop at pi raised to the 6th power. So we're trying to find that sum right there. All right, so this is going to be equal to A, there's A, times 1 minus r raised to the n divided by divided by 1 minus r. We have that. So there's our formula right up there. 1 minus r to the n over 1 minus r all times a. So this is our sum. If we left it in exact form, we would just write it like that. So there's our exact form. We could approximate it. If my math lab says approximate to 10 decimals or 5 decimals, then we could do it. But that is our sum. Gotta love having an assistant. Okay, let's take a look at this one. So you all try this one. So we have a sum from 2 to 50, e over pi to the k. See if you can find that partial sum or that finite sum. Photos of muscle cars on the screen yesterday. Clearly not that one. Maybe.
I haven't gotten that far yet either. I was about to figure that out.
Would you look like? Yeah, it's hard to say. Yeah, so if you can, type it into your calculator and approximate 2 decimals so that we can say the answer. Trying to say the answer exactly with all the pi's and the e's is not trivial. Jeez. How many terms do we have?
2 decimals.
49, so 50 minus 2 plus 1. 49 terms. We will not write out all these terms. How about the a value?
E over pi squared.
Yep. So e over pi squared, we could write it as e squared over pi squared. And how about our common ratio? Yeah, e piths. E over pi. So our formula is going to give us, so I'm going to write it as S sub 49 because S sub 49 means add the first 49 terms. That's what that means. It doesn't have anything to do with the k values. So S sub 49, sum of the first 49 terms, which is all we have here, is going to be a, so e squared over pi squared, multiplied by 1 minus r raised to the n divided by 1 minus r. So there is our unsimplified, gnarly answer. Let's do a little bit of simplification here. Well, let's do it in a minute. Let's do a couple of steps of algebra here. So we're going to rewrite this as e to the 49 over pi to the 49. And then 1 minus e to the e over pi. What should we multiply this fraction by? Right here. What should we multiply that by to clear out those little pesky fractions? Pi to the 49 over pi to the 49. If we multiply by 1, and we multiply by the right form of 1, that will clear out those fractions. So if we needed, for whatever reason, to get an exact answer, not an approximate answer, we're going to multiply by that form of 1. And that form of 1, we'll leave this stuff out in front for a moment until we get to the point where we can simplify everything. So we're going to have pi to the 49 minus e to the 49 divided by pi to the 49 minus e times pi to the 48. And we have a common factor in the denominator of pi to the 48, which we could pull to the front if we wanted to write it as a multiplicative answer. So we have this over pi to the 50. And then here we still have the same numerator. And we pull that. So that's going to be our exact answer in simplified form. And then when we type it in our calculator, what do we get?
5.55.
5.55. Somebody confirm? We have at least 2 people.
Confirm.
Confirm. So 5.55. All right. Geometric series. Not too bad. Any questions on any step there? Everyone 100% sure on what all 3 of those things represent? If we have an infinite series, we don't deal with n because n is going to go up to infinity. But for a finite series, we have to know what n is in addition to a and r. So we always need to know a and r. So now let's take a look at how much easier it is when we have an infinite series, which is just super counterintuitive. We say, gosh, this is going to be easier? So for this one, what is, let's come straight across here. Tell me what a is for this one. 1. And tell me what r is for that one. 1/4. So that tells us that the sum of this series is 1 over 1 minus 1/4. That's what that says. A over 1 minus r. And that's going to be 4/3. 1 minus 1/4 is 3/4. 1 over 3/4. Flip it, and we get 4/3. All right, you all try 28. Find the sum of that series, that infinite series. And the second one's a good one. If it's not 100% clear what your common ratio is, you can just do a few terms and you can see. It starts to become more and more obvious. But. So see if you can come up with that one. A value is 1, and what's the r value? 1 over pi. So all we have to do is know our formula, a over 1 minus r. So this series will add up to 1 over 1 minus 1 over pi. And if you multiply everything by pi, here would be our simplified exact answer. Pi over pi minus 1. That is the sum of that infinite series. The more the merrier, right? If you have an infinite number of terms, it's actually easier to find the sum. The more the merrier. All right, I want you to try 30. There's a little subtlety here. Let me see if you can pick it up. If you are not 100% sure that you're picking off the correct r and the correct a, write out the first 3 terms if you're not 100% sure. What do you think the A value is? 5/4. Do we agree? So we take the initial index, we plug it in. So yeah, totally agree. 5/4. And how about the common ratio? 1/2. 1/2. That's the common ratio. So the 5 is not part of that exponent, correct? So the common ratio is 1/2. There's two ways to rewrite this so that it might be a little more obvious. One way is that we see the 5 is not part of that exponent, so we could rewrite it like this, and then m goes 2 to infinity. Like that. That would help. Or maybe we write out the first few terms. We plug in the 2 and we get 5/4. And then we plug in 3 and we get 5/8, 2 cubed. Then we plug in 4, 2 to the 4 is 16, etc. So if we do that, it's a little more obvious. First term is 5/4, and we see that, oh, we multiply by 1/2 to get to there, and then we multiply by 1/2 again. So if it's not 100% clear, writing out the first few terms is a really good strategy. So our final answer will be A over 1 minus R. 1 minus 1/2 is 1/2. Dividing by 1/2 is multiplying by 2. So we're going to end up with 10/4, which is 5/2. Put that down there. So 5/4 divided by 1/2, that's going to be 10/4, which is 5/2. That is the sum of the series. To stay red. All right, any issues on that one? Make sense? Feeling good? All right, let's try this one. So A is leaping right out at us. No matter what, A is always the very first term in the series. No matter what. Now we have to figure out how we are getting from term to term. So how are we getting there? Looks like multiplying by 3/4. Multiply 1 by 3, multiply 16 by 4. It appears that we're doing that. Let's double check. If we do that with the next one, 3 times 3 is 9. That's good. 64 times 4, that's 128 plus 128. So yeah, 256. So this tells us that the common ratio is in fact 3/4. And so that's how we know it's geometric. It's geometric if you have a common ratio, a common multiplier. That means geometric. Very different than an arithmetic series. An arithmetic series, you have a common addition. So you add 3, add 3, add 3, add 3, or whatever. So geometric, constant multiplication. So this tells us that the sum of the series is A, so 1 over 16, divided by 1 minus R. That will be the sum of the series. Multiply up and down by 16. If we want to clear the fractions, let's multiply by that least common multiple of the denominators. So we're going to end up with 1 over 16 minus 12. One over 16 times 16 is 1. 1 times 16 is 16. 3/4 of 16. 4 goes into 16. 4 times 3 is 12. So this will give us 1/4 as our final answer. So that is the sum of that series. Okay. Any questions on geometric series so far? So these, again, are super helpful because we can actually find S. That's what's helpful about them. We can actually find S. Okay. is this series going to converge? Yes. So remember that our infinite series converge if they're geometric as long as this is true. So R can be positive or negative as long as the magnitude is less than 1. So that means that R itself has to be somewhere between -1 and 1. And the R value here is -9/10, which is greater than -1. So as long as the absolute value of this R value is less than 1, you will have a convergent geometric series. What is A in this case? 1, right? Because the initial K value is 0. So we always use whatever the initial K value is. That's how we find our A. And how about the common ratio? -9/10. So again, if it's not clear, just write out the first few terms. So you plug in 0 and you get 1. Plug in 1 and you're going to get -9/10. Plug in 2. If you square a negative, it goes away and turns to a positive. And you're going to get 9/10 quantity squared, etc. So you can see that you multiply by -9/10, you multiply it again by -9/10. So the sum of this series, sum of this infinite geometric series, will be A over 1 minus -9/10. So the sum is A over 1 minus R. The easiest way here, I think, is to multiply up and down by 10. If you multiply by 10 in the numerator, you have 10, and in the denominator, you'll have 10 plus 9, so we'll get 10/19. Does that make sense? Feels like we're just doing algebra again. But we're adding so fast. We're adding an infinite number of terms. Take that, Zeno. All right, here's another one. Converge or diverge?
Converge.
Do you want to amend your answer?
No, I'm going to stick with converge.
Okay. Anyone else? Federico, what do you think?
Diverge.
Why would you say diverge?
Because the magnitude is greater than 1.
So let's. You see it? All right. So let's make sure that it's in the proper form. So the form of a geometric series is, if we go all the way back to, let's not go all the way back, is AR to the K. The K is all by itself in the exponent position. Not negative K, K. And so what we want is to do this kind of thing. So we can say, oh, this is -1, and all that is raised to the K. So we want to get that K isolated up in the exponent position. So the base, or the R value, is not just -e, it includes that -1. So let's simplify that a little bit. So this is going to be -1 over e raised to the K. So Tyler, you had it. So now we see that the R value is that -1 over e. -1 over e has a magnitude less than 1. So yes, this will converge. So the A value is -1 over e. The R value is also -1 over e. And that tells us that our sum is A, so -1 over e, divided by 1 minus -1 over e. If we multiply everything by e, we're going to have negative 1. 1 times e is e. Negative and negative is plus. That will be the sum of this series. So notice that the sum of this series is negative, right? And because the common ratio is negative 1 over e, the terms are going to alternate in signs. The first term is negative 1 over e. The next term is going to be positive 1 over e squared, and then negative 1 over e cubed. So because the first term is negative, that is why, that's the biggest term in magnitude. That's why we're going to end up with a negative persisting all the way through, because that first term is negative, and it's bigger in magnitude than all the others. All right. Let me see. Let's not do that yet. Let's do one other thing here. I want to talk a little bit about re-indexing. So this starts at 0, this starts at 1. Many times with the geometric series, you are wanting it to start at 0. That's just a common thing. It doesn't matter, though, because as long as you can find r and you can find n. But let's talk for a minute about re-indexing. So let's suppose we have this series that says k equals 2 to n, 2 to infinity. Let's go to infinity. Actually, let's do a finite one first. Let's do a finite one first. Just to make sure. Let's do a short one that we could actually write out if we need to. And let's suppose that we have something in here like 2/3 to the k. So let's suppose we have that series. And we could find a and r pretty easily here. But let's re-index it. Let's suppose, for whatever reason, let's suppose that we really want k to start at 0. We really want that to be the case. What we need to do this is the following. So what we're going to try to do is create a little algebra equation down here. We want to replace the k with something that gives us that. So what we're going to do is replace k with, what can I replace the k with so that when we do a little bit of algebra, we'll end up with k equals 0? Close. If we put in k minus 2 to solve for k, we'd end up with k equals 4. So we'll replace k with k plus 2. If we replace the k with k plus 2, so we take that k, turn it into a k plus 2, subtract 2, we get k equals 0. So if we do that there, we also have to come up here and do 2/3 to the k plus 2. All right. And then we have to figure out our top up here. How many terms does this series have? 5 terms. So 6 minus 4 plus 1, 5 terms. And if we want to have 5 terms over here, what should that end value for k be? 4. So that would be re-indexing it so that it starts at 0. For whatever reason, there are times when you get into differential equations, it'll be really important to be able to re-index things so that you can have things lined up. We'll see it also in this class in a little bit, but that's how you would re-index it. Okay, so let's do, we have 1 minute. Can we do anything in 1 minute? I don't think we can. Yeah, these things take a little bit longer than 1 minute. So let's stop right there. I'll give you a minute. I'll let you have your minute back during the next exam. I'll return it to you. I'll borrow the minute. I'll pay you interest. I'll let you stay 5 extra minutes. I'll pay you a fine interest rate.